Hello, my name is Albena Doicheva. I'm Associate Professor at University of Architecture, Civil Engineering and Geodesy, Sofia. I will speak about shear force in a beam column connection when we have linear distributed load occupying various possible positions on a cantilever beam with asymmetrical cross-section. The part of our presentation is introduction, method, problem, math model, support reaction, result, and discussion, conclusion. In 1967, Hansen and Connor give us first quantitative definition about shear force. This is the horizontal force transferred at the midhead of a horizontal section of beam column connection. This force is separate of few forces like tensile force on top reinforcement bar of beam, compressive force on again top reinforcement bar on beam on the other side of column, and compressive force of concrete. To find these forces on a reinforcement bar was not so easy. That's why in the literature was adopted that these forces are equal to moment on the end of beam divided by distance between reinforcement bar. Then shear force is given in the equation below. In Eurocode, the shear force is a function of area of reinforcement bars and L strength of the reinforcement. But here we don't have information of concrete, and the area of concrete section is not taken into account. That's why we decide to make new math model of beam. The cantilever beam has three support reactions. H2 and H3 are on the level of reinforcement bars, and H1 it's moved on the edge of beam. H1 is the force which modulate the concrete, and this is the result of small forces of small springs which modulate the concrete. H1 move their position, and we can find where is this force with the distance b. As a consequence of the linear deformation in the cantilever beam, a normal axial force N occurs, which is introduced at the free end of beam. For asymmetrical cross-section, we need of a position of centroid, and we use tensile and compressive stiffness of the composite section, which is made of tensile and compressive stiffness of the reinforcement bar and the concrete. We can't say the same of the bending stiffness of the composite section. The support reaction, the solution for support reaction is based on the Menabrius theorem about statically indeterminate system in the first order. The potential energy of deformation taken into account spatial bending combined with tension compression, and there is effect of linear springs of the end of beam. We use three equations of static. For two equations are for forces, and one equation is moment equation. From this equation, we calculate, for example, H2 like a function of H1 and H3. This is one equation which we will use, and the other two equations for calculate H1, H2, and H3, we find from Menabrea theorem. We write the equation of bending moment of a three-part of beam, and using the potential energy of deformation, we find the two equations for our informations. The solution gives us three support reaction. H1 is given here. In the next slide, we have H2 and H3. In all equations, we have information about geometry of beam and about material properties which made it our beam. When we neglect the normal force in the strain potential energy expression, the support reaction are given here in the next slide. Result and discussion. For our calculation, we use beam with length 200 centimeters. The load is linearly distributed with intensity 0.85 kilonewton centimeters, and we have cover of reinforcement bar 3 centimeters. The cross section of bar is 25 to 25. We will use three cases. First case is when we have normal concrete with module of elasticity 1,700 kilonewton centimeter square, and we have 4 and 18 the count of reinforcement bar on a top and bottom position of beam. Second case is when we have high strength concrete and the same numbers of bars. And the third case is when we have again normal concrete, but we have 5 and 18 the count of reinforcement bar on top and bottom position of our beam. The position of H1 we can find using the derivation between H and B. H divided by B is equal to H divided by ZC, position of centroid, and when B is equal to 0, H divided by B is like infinity. The result, in the first, we can see the graphs for normal concrete for first case, and in the first graphs show us the magnitude of H1, H2, and H3 when load is close to the column. When load is close to the free end of beam, then H2 is too bigger. It's about 12 part of our load. The case 2 gives us information that H1 is bigger than first case, and when we have case 3 with more reinforcement, then H1 is smaller, but H2 and H3 again are bigger. How this three support reaction and their parameter change when load move on the top edge of beam can see on the other three graphs. The bigger H1 we have when we use case 2 with high strength concrete. What happened with H2? We can see the parameter of the support reaction H2 for three cases again. The bigger H2 we have when the concrete is normal. And again, we can say almost the same about H3. H3 is bigger when we have more reinforcement bar. And now, what happened with shear force? Now we have equation about H1, H2, and H3, and can compare this information about the equations from literature. And second, we can compare our shear force with shear force from Eurocode. And the result says the next. The first graphs, case 1, with the red line, we can see the shear force calculated by Eurocode. And the blue line is from literature. Our shear force is given by magenta line, and the information shows us that our shear force change their magnitude when crack between beam and column grow, and shear force is bigger than starting the crack grow. The bigger shear force we have when we use high strength concrete. When we use the normal concrete and changing the reinforcement bar, we can see that shear force is smaller than when we use more reinforcement bar, but difference it's not so big. The comparison between our shear force and shear force in the literature says that case 2 with high strength concrete give us a bigger difference, and our shear force is bigger than this of literature. Comparison with Eurocode says that our shear force is bigger again when we have high strength concrete. And our shear force is smaller, so smaller when we have case 3. That's mean more reinforcement bar. And conclusion, a solution has been developed for a cantilever beam with a special arrangement of support. The beam is loaded with linear distributed load, occupying various possible positions. The expression obtained for reaction of the horizontal support give results that clearly show the distribution of forces along the height of beam. They take into account the influence of both the geometry of the beam and the material properties of all its components. This allows us to trace the change in the force entering the beam column connection with different combination of data for the included quantities. The formulas are derived for the limited stage and allow us to determine the distribution of force before and after the appearance of a crack between the beam and the column. The results show that the proposed exact method give results that differ from the accepted one in the literature by about 10%. The difference between the new exact method and the Eurocode varies from -17 to +16%. The Eurocode determined the force that the intent reinforcement can withstand, while the new formulas show how large the actual force are as a result of real load and chosen combination of material properties, taking into account the participation of the concrete cross-section. Thank you for your attention.